Let's talk about equations of lines in 3-space. And while we work through this, it's a good idea to think about the equations of lines in 2-space, or 2 dimensions in the Cartesian coordinate system, where you needed a slope and a y-intercept, or you needed 2 points, or a slope and a point. So similar idea here when we want lines in 3-space, except there's 2 things we're going to need in order to come up with the equation of this line in 3-space. And so one of them is we need a direction vector, a vector that is parallel to this line that we're trying to come up with an equation for. So that's kind of like the slope in 2 dimensions. And then we also need a point. So instead of needing a point and a slope, we need a direction vector and a point. Now, if let's say I have a point on my line, and I'm going to call that point P sub 0. And it'll have coordinates x sub 0, y sub 0, z sub 0. So those will actually be numbers in a particular example. So we'll have the coordinates for one point. And then I'm also going to need a direction vector. I'll call that v. And so this basically tells me the direction of my line. Now what I'm going to do is I'm going to create a vector from the origin to P sub 0, and I have that vector in red. And so that vector is just going to be x sub 0, y sub 0, z sub 0. So the vector from the origin to P sub 0, I just do terminal minus initial, and I'll write it vertically. So I'm going to do x sub 0 minus 0, and then y sub 0 minus 0, and z sub 0 minus 0. So those are really the same 3 numbers as I use for the coordinates of the point. But understand now I'm referring to the vector x sub 0, y sub 0, z sub 0. And now this vector v will have an x, y, and z component. So I'm just going to label the components for my direction vector as v sub x, v sub y, v sub z. Now, let me create any other point on this line. Somewhere, there it is. And that doesn't matter where it is. This represents all the points that are on the line. So I don't have a specific value for each x, y, and z coordinate. This just represents all of them. So I'm just going to use the variables x, y, and z. Much like in the equation of a line, when you write y minus y sub 1 equals m times x minus x sub 1. When we did point slope form, the x and the y variables, we're not plugging in numbers for those. We're plugging in numbers for the y sub 1 and the x sub 1 and the m. So similarly here, I'm just going to label p as x, y, z. Now if I create a vector from 0, 0 to that point p, then I can say the vector from the origin to P is going to be, once again, terminal minus initial, and it's just going to be the vector x, y, and z. All right, so now if I take my vector v and maybe shorten it a little bit or lengthen it a little bit, depending on where the green point P is at, I can make a kind of a triangle with the 3 vectors, the red, the green, and the blue. But I'm going to have to adjust the blue. So depending on where this point P is, maybe it's back over here, then I'd have to multiply my vector v by a negative scalar to flip it over. But there's always some value I can multiply my vector v by in order to create a triangle with these 3 vectors. And so I'm going to use that idea to come up with an equation to represent this line. So as you can see here, I have the red vector, I have the green vector, and I have the blue vector. So if I add the red vector plus, and I'm going to call my scalar t. Why not? So t times v will be my direction vector multiplied by something to make it bigger or smaller, to lengthen it, maybe to flip it in the opposite direction, whatever. So my red vector plus the blue vector should equal my green vector. And now that's an equation. And so that's the idea behind coming up with the equation of a line. So the red vector, x sub 0, y sub 0, z sub 0, plus a scalar, t, times my blue vector, my direction vector, v sub x, v sub y, v sub z, is going to give me the green vector, and that's just x, y, z. So now it's really important that you're understanding here that these values, x sub 0, y sub 0, z sub 0, they come from the point that was given to me in the problem. They come from this point here and its coordinates, and we made a vector from 0, 0, 0 to that point, and that's how we got the red vector, x sub 0, y sub 0, z sub 0. And then the components of my direction vector, those will have specific numbers for a given problem, because they'll give us a direction vector. And then I'm going to multiply that by some scalar t. Now, if I rewrite this a little bit so they're vertical, what I have here is the vector equation of a line. And in IB, you'll see the notation r equals a plus lambda times b. So lambda is really the same thing as what I'm calling t, my parameter, and a is the point that was given to us as a vector, and then b is the direction vector. So, but anyway, that's referred to as the vector equation for a line. Now I could manipulate this a little bit from what we know about vectors, and I could look at, if these vectors are equal, that means the x components match, the y components match, and the z components match. So I can actually combine the red and the blue vector times t, and put that all together in a single vector on the right-hand side of my equation. And then if I separate each of these components, and I set x equal to the x sub 0 plus t times v sub x, and then the y component, set that equal to the y component on the right, etc., I actually can come up with three equations: what x equals, what y equals, and what z equals. And remember, we have specific numbers for x sub 0, y sub 0, z sub 0. That's the point that was given to us in the problem, the x, y, and z coordinates. And then I have numbers for v sub x, v sub y, v sub z. That's our direction vector. And then t is another variable. This is referred to as the parametric form. So we have the vector equation, we have the parametric equations for a line. And then I could rearrange these even further, and if I solved each of these equations for t, if I got t by itself, it would be x minus x sub 0 divided by v sub x, and then y minus y sub 0 divided by v sub x. And same thing here. If I solved all three of these equations for t, then I could set those equations equal to each other, and thereby eliminating the t. And I have this form, and this is referred to as the symmetric form, and in IB they call it the Cartesian equation. So we have three different forms. We have the vector equation, we have the parametric equation, and we have the symmetric equation, or sometimes called Cartesian equation. So let's look at some specific examples. Find the parametric equation, so that's the first thing you should understand. Just like in Algebra 1, find in slope-intercept form, or find in point-slope form, or find in standard form, the equation for the line that passes through the point. So here's the point, and it's parallel to, that's my direction vector. So I have a point, and I have a direction vector. Okay, so if you remember, I'm just going to go ahead and I'm not going to put it in parametric form first. First, I'm just going to write x, y, z. equals, and I use the numbers from my point, plus t, or lambda, whatever you want to use, and then the components of my direction vector. And so that's the vector equation for the line that they're referring to. And then if I put it in parametric form, that means, let's write it in different colors. So what I have is I have x equals 3 minus t, and I have y equals 2 plus 3t, and then z is equal to 1 plus 5t. And there we go. So there's your parametric form. What if we wanted to do the symmetric form or the Cartesian form? Well, then we just solve each of those green equations for t and set them equal to each other. So for the first one, I'll have x minus 3 divided by negative 1. That equals t. And in the second equation, t is equal to y minus 2 divided by 3. And in the third equation, z minus 1 divided by 5. And so there's your symmetric or Cartesian form. All right, let's look at another example. Find the parametric form of the line containing, So remember, we need a point and we need a direction vector. They're not giving me a direction vector, but they did give me a point. They actually gave me 2 points. So just like in Algebra 1, if you're used to being given the slope and a point, and then all of a sudden they say, hey, here's 2 points, you had to do a little extra work. You needed to use those 2 points to find your slope. Well, I'm going to use these 2 points to come up with a direction vector. So I'm simply going to get the vector AB, or you could do BA, it doesn't matter. The vector AB is going to be terminal minus initial, 3 minus 2 is 1. Negative 1 minus 4 is negative 5. And 1 minus a negative 3 is 4. So the vector AB, now I have a direction vector, and then I can use either point. It doesn't matter. So let's say I use point A, and we want this in parametric form. So I'm going to have x equals 2 plus 1 times t. So I use that number, and I use that number. Now I'm ready to write the y equation. So now I'm going to be using the 4 and the negative 5. So y is equal to 4 minus 5t. And finally for z, it's going to equal negative 3 plus 4t. Because I used the z component and the z coordinate for my point and my vector. Now what if somebody else said, whoa, wait a minute, I don't like using A, I'm allergic to A, I'm going to go with point B instead. How does that change? Well, all that does is changes these numbers. Instead of point A, I get point B. So it's going to become, we're going to have 3 plus 1t. Yes, you don't have to write the 1. And then you're going to have negative 1 minus 5t, and z is equal to 1 plus 4t. And so you can see it looks like we have 2 totally different answers, but it just depends on which point we're using, the A or the B point, to write our equation. Now also, we did vector AB. We could have done vector BA. How would that affect it? Well, if I use vector BA, that's just going to change the signs of those components, and then instead of a plus here, that will be a minus, this will be a plus, and that'll be a minus. So there's actually, and the same with the purple equation, so there's actually 4 different possible answers for this, depending on what route you want to go. But any one of those 4 would be fine. All right, and then what if I asked you to write the Cartesian equation, i.e. the symmetric form? Well, let's use the purple one. since I have that available here. So if I solve the x equation for t, I'm going to get x minus 3 divided by 1. Solve the y, I'll get y plus 1 divided by negative 5. And then z minus 1 divided by 4. And there's my answer for that. All right. So once you get the hang of it, it's pretty straightforward. Let's try one last thing I want to mention here. So find the coordinates of 3 different points on the line. So now what I'm giving you is actually the parametric equations for the line. And I want to know, well, tell me a few different points on this line. Well, from what we've learned, automatically we know that 3, negative 1, 1 is one of the points. Now notice I get that when t is equal to 0 in my 3 equations. What if I set t equal to 1? Then x is going to become 3 plus 1, which is 4. Y will be negative 1 minus 5, which is negative 6. And the z equation will be 1 plus 4, which is 5. What if I set t equal to 2? Then x is going to become 3 plus 2. Y is going to be negative 1 minus 10. And z will be 1 plus 8. And so you can see by picking different values of t, I can get different points on my line. And remember what t represented. Let me go way back to the beginning here. I have this v, my direction vector. When I multiply it by a scalar, it's going to make it smaller or bigger. And then when I pick my second point on this line, wherever it was, right there, and I'm trying to come up with the sum of the red and blue vector to equal the green vector, by multiplying v by a scalar, that scalar t, that's either shrinking it or expanding it so that it gives me the vector that goes from the terminal point of red to the terminal point of the green. And so that's what that parameter t does for us. And likewise, where I said that in the last example where I could have different equations, notice for the green equation, I get the point 2, 4, negative 3, and that's when t equals 0. Well, I should be able to come up with that point 2, 4, negative 3 on my purple equations, but it's going to have to be for a different value of t. And so what would that be? Well, let's see. It looks like if t is negative 1, then x would be 2, y would be 4, and z would be negative 3. So I can get the same point, even though those equations look different. It's just it's going to be for different values of t. All right.